Alrighty, everybody, we just got our okay to start our planetarium show. So, welcome everyone to the Morrison Planetarium. And real quick, I'm going to change the lighting in here so we get our eyes a little bit more adjusted to the darkness. And once again, welcome folks to the Morrison Planetarium. My name is Christian. I want to be your planetarium presenter for this show this afternoon. And I'm very excited to have y'all here today because, folks, you're my favorite place in this entire universe, the Morrison Planetarium. And the reason why is because everything that you see in purple right now in the dome is one really big screen, thanks to the help of 6 different projectors hidden throughout our planetarium dome. If you're looking for our projector system, it's hidden just below that purple glow. And folks, I am very excited to announce that the show that we're about to watch right now is different from all the other ones that we've done here today, and it's a personal favorite of mine. This one's called Tour of the Universe. And with Tour of the Universe, you're going to hear my voice for the next 30 minutes because this is completely live as I fly you through space. And what this show entails, well, we're going to be starting off pretty close to the Earth, and we're going to be zooming all the way out to the very edge of the observable universe. So hopefully by the end of the show, you won't have an existential crisis of where we are in space. But just a heads up, we're pretty small in the grand scheme of things, so just a forewarning. And before we get started, I do have to go over some quick house rules just so that we're all on the same page and have an enjoyable time. First off, folks, there's no food or drinks allowed in. If you brought any snacks, now's a good time to put those away. We want to keep the theater as clean as possible. Also, folks, if you brought any cell phones, smartwatches, anything that produces really bright white light, now's a good time to put it away for the next 30 minutes, as these can be very distracting and takes away from the planetarium show experience. And folks, if you need to leave early during the show, you're welcome to do so. The exits are always going to be at the top of the planetarium, so always make your way up the stairs to exit. And we understand that the staircase is quite steep for some folks. You're going from the first floor all the way to the third floor. If that poses a challenge for you, just remain seated. Once the show's over and we get the majority of folks up to the top, we'll have someone escort you to a lower exit. So just stay seated for a bit longer. And last but not least, folks, this show is very immersive thanks to our 75-foot dome above us. If at any point during the show you start to feel overwhelmed, you start to experience motion sensitivity, there's a really quick and easy trick to ground yourself. All you got to do is close your eyes, take in a few big deep breaths, then your brain will remember that you're sitting in a planetarium in San Francisco and not hurtling through the universe, at least not more than the usual. Hee hee hee. But with that being said, it looks like we're ready to go. So I invite y'all to sit back, relax, and let's begin our tour of the universe. Alrighty, folks, we're going to be starting off pretty close to the Earth. Not quite on it. We can see the city lights just down below. We're in the nighttime side of the Earth. And we're starting off at this really cool spacecraft right in front of us called the International Space Station, or the ISS for short. And a lot of people tend to ask me, hey Christian, what's the International Space Station? I hear about it all the time in articles and news, but I don't really know what it is. Could you explain it for me? Well, of course, folks, the International Space Station is a research facility. It's a laboratory that orbits around our planet Earth. And they conduct all different types of experiments all the way up here with less gravity. Some of the experiments that they'll conduct are things like what happens when you try to grow plants in space? Do the roots grow? Which way do the roots grow with less gravity? Another one is one of my favorites is what happens when you try to spark a match in space? Does the flame act the same? Does that act differently? And also, another one is they had 2 identical twins. One twin lived on Earth for about a year, the other one lived on the International Space Station for a year. After the year, they compare and contrasted. Turns out when you live in space for a long period of time, you tend to age a little bit slower, but not only that, you also lose a lot of muscle because you don't have gravity constantly working down on your muscles all the time. So those are just some of the experiments that they've conducted up here in the International Space Station. There's a whole lot of them if you want to explore them in more depth. And also, folks, looking at the spacecraft here, this thing looks really big here in our planetarium dome. But the International Space Station's only about the size of an American football field. If you've never been to an American football game, don't worry. You can also use the entire California Academy of Sciences, the museum we're sitting in right now. That's about how big it is. And also, what's really impressive is that this thing is going incredibly fast. It's going a whopping 17,000 miles per hour, where it orbits once around the Earth every 90 minutes and experiences 16 sunrises and 16 sunsets a day. Whew, how romantic. And also, folks, this looks really far away from our planet Earth, but it's not that far either. The International Space Station's only about 225 miles above the surface of our world. 225 miles. That's not too bad for us Californians. That's like going from San Francisco to Santa Barbara, a nice little road trip to get away with the family for the weekend, so not too bad. But to tell you the truth, folks, this is as far as we put humans into space nowadays, only 225 miles above the surface of our world. The reason why, well, it's quite costly to travel in space. Gotta buy yourself a rocket ship or build yourself one. And then once you get your hands on that, you gotta buy so much rocket fuel. You're gonna need so much rocket fuel, gotta be able to escape the Earth's gravity. And once you acquire that, you have to also account for all the food, water, all the air you're gonna be breathing while you're up here in space. So the bill gets quite costly quite rapidly. But the International Space Station, folks, is just the first stop in our tour of the universe. So now we're going to see it slowly fade away to the city lights down below. Before we lose track of it, I want to add a nice little orbital path so you can see it as it disappears. And it looks like we're hovering just above Australia right now. And now we can see our entire Earth in all of its glory. And folks, I want to let you know that the space program that we're using here inside the Morrison Planetarium is something that you can go home and fly through space if you'd like to. This one in here is called OpenSpace. So if you go to your favorite search engine, type in OpenSpace project, you'll come across the link where you can download this. And it's a whole lot of fun. Although, just a warning, this program is in its beta phase, so we may come across a few bugs and glitches. If we do, I'll point them out. Hopefully, we can look past that. But what's also really cool is that this program uses a whole lot of processing power. It uses almost real-time data from satellites. So if you have an older computer, you may want to rethink it. It may overwhelm your computer. But if you got something new, like a gaming computer, give it a try. It's a whole lot of fun. And if you're a person like me that doesn't want to download anything, you just want to fly through space, we also have another great alternative called NASA's Eyes. Just like the human eyeball, type in NASA's Eyes, and you can fly through space without having to download anything, and it's so much fun. But in here, we're using OpenSpace. But now that we got a sense of what we're using in here, let's make our way over to our nearest natural neighbor to us in space, the moon. And folks, we humans have been to the moon before. That was between 1969 and 1972, thanks to NASA's 6 Apollo space missions that brought a total of 12 incredibly lucky guys to walk on the surface of the moon. They got to conduct science, and of course, they had some fun up here as well. They got to play some golf. But again, the last time we sent humans to the moon was 1972, a little more than 50 years ago or so. But don't worry, folks, we humans are making a return trip back to the moon in the next few years, thanks to NASA's new space mission called Artemis. Pretty much with Artemis, NASA wants to send humans to Mars, but before we send humans deep into our solar system, we gotta figure out exactly how we're gonna be living out here in space. So the moon is the perfect stepping stone how we're gonna figure that out. And what's really cool is that they're gonna be sending the first woman to the moon, but not only that, they're also gonna be sending the first person of color to the moon, but not only that, they're also gonna be setting up lunar bases throughout the moon. Pretty much our technology has greatly improved in the last 50 years, so we're able to do much more science in a much more compactable, smaller size. And one place that we definitely want to set up a lunar base is going to be the south pole of the moon. The reason why is we found ice there, and ice is going to be very helpful because we can melt that, pass electricity through it, and then we can get hydrogen and oxygen, and both that stuff is very valuable when you're out here in space, far from home. But again, folks, we humans should be making a return trip back to the moon in the next few years, so look out for any news about Artemis. And folks, when we look up at the moon here on Earth, sometimes the moon feels incredibly close to us. Feels like you can reach out your arms and touch it. But the moon's really far away. It's about 240,000 miles away from our planet. 240,000 miles. Some of the adults in this room may have a car with that many miles on it. And if you take better care of your car than I do, you can even imagine driving to the moon if you drove for about 4 months nonstop, going about 80 miles per hour. Although I wouldn't recommend it, the roads out here are poorly maintained. Hee hee hee. And from here on now, folks, we're going to need to use a more useful measuring stick because at this scale, using miles is kind of like using inches to describe the distances between cities because space is so big. So astronomers use a more convenient measurement known as light speed. And light travels at a mind-boggling speed of 187,000 miles per second. That's roughly about 300,000 kilometers per second. So while it took the astronauts more than 3 days to reach the moon, traveling faster and farther than any human has done so ever since, it only takes light 1.5 seconds to cross that distance at the speed of light. That's kind of like a short pause in conversation. But at last, folks, it's time for us to leave the moon behind, so everybody say bye bye, moon. See you later. Hee hee. So wholesome. And now, folks, we're going to see the moon and the earth as they start to slowly fade away in the vastness of space. And before we lose track of the moon, I want to add some nice planet trails so we can see where everything is in space, because again, space is quite large. So we have a nice moon trail, and we're going to see our earth trail as well. And folks, on our journey, we're going to be traveling much faster than the speed of light. We're going to be traveling at the speed of the human imagination, thanks to the help of computer models like OpenSpace showing us the most accurate images and information available to us. And now the nearest star to us, the sun, should be coming into view. So here comes the sun. Do. And also, folks, the sun is incredibly far away from us here on Earth. It's about 93 million miles between us. 93 million miles. That is a good distance away. And again, we're the third rock from the sun, so we just left Earth, which is over here on the right-hand side. Third rock from the sun, 93 million miles between us. In order for sunlight to travel that distance, it only takes sunlight about 8.5 minutes at the speed of light. And this is important because let's say the sun was to turn off all of a sudden, no more sunlight was being emitted. That last bit of sunlight will travel 8.5 minutes at the speed of light, 93 million miles, and then all of a sudden the daytime on Earth would become nighttime. And again, this is such a cool concept because let's say we're looking at a star that's 70 light years away. We're looking at that star as it looked like 70 years ago. Because in order for us to see that sunlight traveled, or that starlight took 70 years to get to us. So when you're looking at really far away objects in space, it's like looking back in time, which is pretty cool. But now that we have a nice bird's eye view of our solar system, let's do a quick refresher of what we have here. Right in the middle of our solar system, we have the biggest thing, the star, our sun. Closest planet to the sun, we have Mercury, then we have Venus, Earth, that's us, and then Mars, the red planet. So these are all the rocky terrestrial planets. These are places where we can actually land a spacecraft on, although a couple of them are really hot, and you wouldn't really want to do that. And then past Mars, we have this really cool thing called the main asteroid belt. And this is what it looked like if we highlight all the asteroids in the asteroid belt. There is a lot of them. And then past the asteroid belt, we have the really big planets, the gas giants, the Jovians. We have Jupiter, the largest of them all. Then we have Saturn, famous for its rings. And then we have our icy gas giants. We got Uranus, the funny one, and Neptune. And of course, we can add everyone's favorite and lovable dwarf planet, Pluto. So here comes the orbit of Pluto on screen. On the very top left, right over there. And a lot of people don't realize that Pluto hangs out here in this outer part of our solar system called the Kuiper Belt. And you're probably wondering, what's the Kuiper Belt? I've never heard of that before. Well, folks, this is the Kuiper Belt. So way past the orbit of Neptune is the Kuiper Belt region, and this is like a second asteroid belt all the way out here. And what you're mostly going to find are icy asteroids and short period comets that don't stray too far away from the sun. And what's really cool is that we found more than 400 objects here in 2006. Some of these objects were bigger than Pluto, so we couldn't call all this stuff planets. So all the astronomers on planet Earth had a great big meeting. They had to figure out what exactly you need to be considered a planet. And they came up with 3 criterias. And folks, that was the day in 2006 when Pluto went from being a planet to a dwarf planet. And that's the really cool thing, because as our technology improves, we're able to see much smaller objects much further away. And once that happens, we're able to reclassify and redefine things. So that's why that's really cool thing about science. It's always changing and updating. But I'm going to put away the Kuiper Belt because that's just a whole lot to look at. And now I'm going to be putting up on screen the many different spacecrafts we sent out in the 1970s to explore our solar system. We have the trajectories of Pioneer 10, Pioneer 11, Voyager 1, and Voyager 2, and the latest of them all, New Horizons, which flew by Pluto in 2015. Now, all of these spacecrafts are all traveling fast enough to escape the sun's gravity and leave our solar system behind. But even the most distant of these robot adventurers, Voyager 1, has not traveled as far as light travels in a single day. In order for sunlight to travel all the way out to the orbit of Pluto, it takes sunlight about 5 hours at the speed of light. 5 hours, not too bad. But now, folks, it's time for us to leave our planetary scale behind us because now we're going to be heading into interstellar space, the space between the stars. Distance now becomes so immense, it's going to take us about 4 years at the speed of light just to reach the next star system to us, the Alpha Centauri system. And now our starlight becomes one of many stars out here in the star field. And hey, look at that. That's the first. We just flew by Alpha Centauri. So it's the star on the left hand side that's moving the most. And again, we're right in the center of our screen, our solar system. And again, 4 years at the speed of light just to reach the next star system to us, folks. But that doesn't really put into perspective of how long it would take us humans to travel that distance. Well, folks, if you're getting a rocket ship of today's capability, make your way over to Alpha Centauri. It's going to take you about 8,500 years to make that trip. Whew, and that's just a one way trip. But let's stop and consider whether humanity has made its presence known beyond our solar system, folks, because now we're going to be stepping inside something called the radiosphere. And again, we're now inside something called the radiosphere, and this represents the current limits of the most distant radio signals humanity has ever broadcasted, or rather leaked into space. And it extends about 90 light years in all directions, emitting out from the Earth. This first began in the early 1930s with strong radio waves, early television, and radar signal, and then later the detonation of atomic weapons. All this stuff is emitting electromagnetic radiation strong enough to escape the Earth's ionosphere. And humans were broadcasting well before that, but the earliest radio was not quite powerful enough to escape the Earth. And, and since all these signals are electromagnetic, they are traveling at the speed of light. So this is kind of like humanity's electromagnetic footprint in the universe. And of course, folks, the radiosphere is constantly expanding at the rate of 1 light year per year. So is anybody out there listening? And now, folks, I'm going to be adding these many markers onto the screen. These many markers indicate the many thousands of stars astronomers have discovered over the last 30 years, which has at least one or more planets orbiting around them. We call these planets exoplanets, and we're looking for any of them that are Earth-like with conditions suitable for life as we know it. So far today, we found more than 5,000 confirmed exoplanets in the nearby vicinity to us, 5,000 other worlds besides our own. And that number is going to be increasing as the years continue because we have spacecrafts where their whole purpose is to find as many exoplanets as possible. Now, to answer if any of them are Earth-like with conditions suitable for life, well, we can't answer that question quite yet, but new spacecrafts are being developed right now, so it's going to be a few years before we can answer that question. But the more important point here is that quite a few of these planetary systems are within that 90 light-year limit of our radiosphere and could have potentially received our signal. However, since radio waves travel at the speed of light, if there is anybody that's out there able to listen in and answer back, the communication delays between hellos could be decades in time. Now, to give you an example, let's say we fly back into our radiosphere. We live in a star system on the far left side. Let's say, pick this one here. And we find an alien civilization somewhere towards the middle. Let's say this one here. We shoot them a text message. We say, hey, we're humans. We live over here in this part of the universe. Takes 60 years to get to them. They listen in, answer back. Another 60 years to get their response. Folks, that is a 120-year conversation in the making. Whew, and I can barely wait for a text message from my friend. But of course, folks, planetary systems beyond the radiosphere, more than 90 light years away, have not heard from us yet, but eventually they will, as the radiosphere is always growing, but it becomes weaker as it does. And I want to put away our exoplanet markers, but I'm going to leave our radiosphere up on screen, because as huge as humanity's electromagnetic footprint is, it is nothing compared to our Milky Way galaxy. All right, folks, we're now looking down at our Milky Way galaxy. This is the galaxy we live in. And I've got to ask, can anybody see their house from here? Hee hee hee. Just kidding. And folks, our Milky Way galaxy is really big. If you wanted to cross it from one side to the other, it's going to take you about 130,000 years at the speed of light. And our galaxy is so huge, we estimate that there's at least 300 billion stars in our galaxy. If our recent discovery of so many exoplanets just within our small neighborhood within this vast star city is any indication, there could be billions of planets, potentially millions of Earth-like planets throughout our single galaxy. And before we leave the Milky Way, I want to show you what it looks like from a sideways perspective. You're going to notice that our Milky Way kind of looks like a big pancake in space. It's really flat from the side. And this is important because when astronomers and scientists want to learn about the universe, it's much easier for them to point their telescopes galactically north and galactically south instead of looking to the plane of the Milky Way, which has planets, stars, gas, debris, things that block their view of the universe. So keep that in mind. That's going to come important just a little bit. But folks, the Milky Way galaxy is only one of many hundreds of billions of galaxies that comprise the known universe. So in this giant leap, every single point of light that you're now going to see no longer represents a star, but rather the location of an individual galaxy. Each galaxy containing hundreds, perhaps trillions of stars. And we live in a local galaxy group which contains about 30 galaxies large and small. Also includes the nearest large spiral to us, the Andromeda galaxy, only 2 million light years away and just next door, and heading right for us. We're going to get to know it pretty intimately in about 5 billion years, so mark your calendars. And as we continue zooming out, expanding out, you're now going to realize that galaxies are not evenly distributed throughout space. Instead, galaxies like to clump together in large groups and clusters, or they like to avoid each other where there's very few galaxies or voids in space. So we have some nice galaxy clustering towards the center of our screen. We got some over here on the right-hand side. We can see very few galaxies towards the north or voids in space. So you can kind of think of galaxies like people. They like to hang out together or they like to avoid each other. And folks, this picture that we're now looking at represents the closest 30,000 galaxies to us in space over 300 million light years across. We got to give thanks to an amazing astronomer by the name of Dr. Brent Tooley, who compiled this amazing representation thanks to the work of dozens of other astronomers working beside him over decades in time. So big shout out to Dr. Brent Tooley. But folks, we now have automated systems that are mapping even the most distant galaxies. So now, folks, we're about to see the very large-scale structure of the universe. And remember, folks, every single point of light that you're seeing, that's not a star, that's an individual galaxy. Whew. And as we start to swing around, you're now going to realize that the large-scale structure of the universe is not in the shape of a bow tie or a butterfly. Remember when I just mentioned that we live in a big flat spiral disk of our Milky Way galaxy? Well, if we line up our Milky Way, it would line up just down the middle vertically like so. And again, we like to point our telescopes galactically north and galactically south. But astronomers still want to make sure that there was galaxies through the plane of our Milky Way, so we have this nice purple survey of galaxies. You'll notice that we're still able to find them, just not as many and not as far. Pretty much we have to wait for our technology to improve, and once that happens, we'll be able to map out all these gaps that haven't been filled in yet, so it's just a matter of time. But it looks like we're running close out of time on our tour of the universe, folks. 30 minutes is just not enough, so let's continue pressing on, because now we're going to be encountering these really distant, faraway objects known as the quasars. And the quasars are going to be represented by orange dots on either side of the large-scale structure of the universe. And quasars are short for quasi-stellar radio sources. And these blazing objects are all billions of light years away. So now we're looking so far back in the depth of time and space that the most distant quasars represent the universe at a much earlier age. We're nearing the very beginning of galaxy formation. In other words, with the quasars, we're viewing a sort of awkward, gawky teenage version of the universe. And before there was a teenager, there was a baby. So let's press back to a time before quasars, before planets, stars, and even galaxies began to form. Folks, we're about to see the very edge of the observable universe. And here we are, folks, at the very edge of the observable universe, and what we're looking at is something called the cosmic microwave background image, or the CMB image for short. And all evidence indicates that the universe that we live in is about 13.8 billion years old. This is data compiled by Planck and other radio telescopes. And this is a very baby version of the universe, only 380,000 years after the Big Bang occurred, where space and time began. And this isn't your typical photo either. Instead, this is a temperature density image, where the light echoes of the Big Bang are color coded, with the lighter areas corresponding to the hottest, least dense regions, and the darker areas, the coolest, densest regions. And these fluctuations in temperature and density are extremely tiny. They vary no more than 1 part per 100,000. But these really tiny differences eventually gave rise to the large scale structure of the universe that we saw moments ago, that clumping and clustering of galaxies everywhere. Figuring out just how that happened is one of the larger challenges for cosmological research today. Though our view here is of the outer edge of the known universe, folks, the earliest light visible to us, that radiation actually persists all around us. It permeates the universe, stretching and cooling as the universe expands over billions of years of time. But folks, we only have one direction left to go. Um, and since we traveled as far back as the law of physics can physically allow us to go, so we're going to make our trip back to planet Earth. So let's find a nice entry point through all these quasars and galaxies. This looks like a nice spot. And let's make our return trip back to planet Earth, everybody. Alrighty, everybody, we're crossing an expanse of over 13 billion light years. We present you with this view of our universe and the latest in cosmological and astronomical information. We're covering eons and observing objects billions of light years apart. We live in a golden age of astronomy with new generations of telescopes and spacecrafts that are extending the reaches of our eyes, preparing for the eventual race between the advancement of technology and the accelerating expansion of the universe. And with that thought, everybody, I want to remind you all that astronomy is for everyone. You don't need to be a rocket scientist to enjoy the beauties and wonders of our universe. All you need is the night sky, and if you can, get away from the lights of our cities and look up. Even a good pair of binoculars makes for a decent first telescope, and there's astronomy clubs all around the world that invite people just like you to look through their telescopes and peer into the great beyond, allowing you to partake in the wonders that our universe has to offer. Now, astronomy as a hobby can offer an endless supply of satisfaction, and I do hope you'll join us, those who dream amongst the stars. But it looks like we're making our way back into our Milky Way galaxy. And we're heading straight for that radiosphere, folks. And folks, if you want to share this experience, this show that you just saw, you can watch this exact show and share with friends and family if you go to the Morrison Planetarium's Facebook or YouTube page. So you can always share the show if you like. But now it looks like we're making our way back into our solar system, our star system, folks, passing those spacecrafts we sent out in the 1970s to explore our solar system, passing the orbit of Pluto and the Kuiper Belt region, and making our way to the third rock from the sun, our homeworld, planet Earth. All the people that we know, love, ever learned about in history all lived on this one planet. And now, folks, we're about to pass the orbit of the moon, the furthest we've ever sent humans out into outer space. And now we're going to make our final approach back to planet Earth. And I want to thank y'all for stopping by and watching Tour of the Universe with me. I hope you had a great time. But hey, look at that. We made it back home safe and sound just in time for dinner time. And that's all the time that we have today, folks. Thanks for stopping by, and I hope you get home safely.